Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is capacitor charging featuring Thevenin's theorem. Our objective is to examine slightly more sophisticated capacitor charging scenarios necessitating the use of Thevenin's theorem. It should go without stating that this lecture operates under the presumption the viewer is intimately familiar with the capacitor charging process and Thevenin's theorem, as illustrated in the capacitor charging and the DC Thevenin's theorems lectures, both available at the Big Bad Tech channel. Additionally, it is presumed the viewer has watched the capacitor charging with initial conditions lecture, also available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. Are you bored with capacitors yet? If not, you should be. We've discussed all sorts of capacitor scenarios, and the process by now should feel pretty formulaic. If it doesn't feel formulaic, you're doing it wrong, and you need to revisit and review the aforementioned lectures until it does. If you haven't figured out the formula just yet, here it is. Determine the start point, determine the end point, determine the time constant. Pull the pin and throw it. Really, there's only two possibilities for any transient analysis scenario. Does an electrical property go up or does it go down? Sometimes there's a gradual and predictable change, like voltage across a capacitor during the charge and discharge process. And sometimes there's a dramatic and instantaneous reversal, like current into or out of the capacitor during the charge and discharge process. While charging, we learned that current rushes through a resistor and into a capacitor. During the charge process, voltage across the capacitor rises. Current into the charging capacitor experiences an initial spike, which decays to zero after 5 time constants, at which time the capacitor is considered fully charged. When discharging, current rushes out of the capacitor and through a resistor. During the discharge process, voltage across the capacitor drops. Current out of the capacitor experiences an initial spike, which decays to zero after 5 time constants, at which time the capacitor is considered fully discharged. Any voltage experienced by any resistor during either the charge or discharge process is simply the consequence of the incoming and outgoing current experienced by the charging and discharging capacitor. Importantly, voltage across the capacitor, whether charging or discharging, never undergoes a disjointed instantaneous transition or sudden reversal in polarity. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Perhaps the most challenging aspect of transient analysis you've yet encountered is the thick mathematics jungle through which you had to hack to determine instantaneous values at specific times and determine the exact times which satisfy given conditions. Hopefully all that arduous hacking is behind you now and you find yourself capable of performing these mathematical tricks with ease. All this training has been in preparation for slightly more sophisticated capacitor charging scenarios necessitating the use of Thevenin's theorem. Not every charging occasion is a simple series circuit, nor is every occasion as clear-cut as we've thus far examined, and sometimes more complicated scenarios present themselves. Consider the classic charge and discharge setup we've examined in numerous illustrated examples. That of a DC source, in this case 12 volts, a capacitor, in this case 15 microfarads, and 2 switches, where switch 1 serves to charge the capacitor through R1, in this case a 200 ohm resistor, and switch 2 serves to discharge the capacitor through R2, in this case a 400 ohm resistor. When charged through R1 by closing switch 1 for 15 milliseconds, we observe the classic charge behavior, that of an initial current spike into the charging capacitor and rising voltage across the capacitor. When switch 1 is open and discharged through R2 by closing switch 2 for 30 milliseconds, we observe the classic discharge behavior, that of an initial current spike out of the discharging capacitor and falling voltage across the capacitor. In all of our previous analyses, with some minor variations, one switch and one series path serves to charge the capacitor, and the other switch serves to discharge the capacitor. My question to you is this: what happens if we're presented with an initially uncharged capacitor, an occasion in which the initial voltage across the capacitor is assumed to be 0 volts, and both switch 1 and switch 2 close at t equals 0? The answer is something different entirely. From the source's perspective, it sees not a simple series charging circuit, but rather a series parallel circuit, where the capacitor in question is in parallel with R2, and this parallel combination is in series with R1. From the capacitor's perspective, some of that current ordinarily intended to charge it is instead diverted through R2. Given R2 and the capacitor are in parallel with one another, the voltage across these two elements must be the same at all times. One could use models of the initial and final conditions to perform a time-variant series parallel circuit analysis of this circuit. However, easier, more convenient methods exist, and from there electrical properties can be mapped back to the original series parallel circuit. Allow me to demonstrate. Perhaps the easiest and most direct means of analyzing this slightly more sophisticated charge scenario is through the use of Thevenin's theorem, and the capacitor sees the Thevenin equivalent circuit of the more complicated series parallel circuit. Again, the easiest means of analyzing this scenario is through the use of Thevenin's theorem, where the capacitor in question is assumed to be the load of interest. The purely series Thevenin equivalent circuit can then be used to determine the electrical properties of the transient charging process for the original more complicated series parallel circuit. Again, I need to make it perfectly clear that this is not the Thevenin's theorem lecture, but rather this is the capacitor charging featuring Thevenin's theorem lecture, and assumes you can confidently wield Thevenin's theorem with little difficulty. I will not demonstrate nor explain the steps used to derive the Thevenin's equivalent circuit, but rather unsheath Thevenin's theorem and swing it wildly about my head. Speaking of which, do you know Thevenin's theorem? Prove it. See if you can determine the Thevenin's equivalent circuit seen by the capacitor when it is assumed to be the load of interest. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. When the capacitor is removed and replaced with an open circuit, the voltage across the terminals of interest would be 8 volts. This is the Thevenin equivalent voltage. When the capacitor is removed and replaced with an open circuit, and the voltage source removed by substituting a short circuit, the resistance seen at the terminals of interest would be R1 in parallel with R2, or 133.3 ohms. This is the Thevenin's equivalent resistance. By the way, if you obtain different values for the Thevenin's equivalent voltage and the Thevenin's equivalent resistance, you don't know Thevenin's theorem and are simply not qualified to continue with this lecture. Save yourself the heartache and frustration by turning around now and getting yourself some Thevenin's theorem from the Thevenin's theorem store if this describes your sorry state. If you already got yourself a bag full of Thevenin's theorem, by all means continue. The Thevenin's equivalent circuit is therefore an 8 volt DC source in series with a 133.3 ohm resistor in series with the originally uncharged 15 microfarad capacitor. This simple series circuit is a far easier goat to wrestle than the original series parallel circuit. Once we've conducted transient analysis of the charging process using the Thevenin's equivalent circuit, we can then map these electrical properties back to our original series parallel circuit. Speaking of which, since you've had ample experience analyzing these types of charging circuits, analyze this circuit. If you need a task list, here it is. Determine the time constant for the charging process. Determine the initial conditions for the capacitor. Determine the final conditions for the capacitor. Determine the time-varying expressions for voltage across the capacitor and current through the capacitor. And finally, draw plots of voltage across the capacitor and current through the capacitor for a full charge of 5 time constants. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. The time constant for this simple series circuit is the resistance value times the capacitance value. Substituting the given values of 133.3 ohms and 15 microfarads, we obtain a time constant of 2 milliseconds. This implies the charging process will complete after 5 time constants, or 5 times 2 milliseconds, or 10 milliseconds. At t equals 0, the initially uncharged capacitor can be modeled as a short circuit or low resistance path. Using this simplification, our initial conditions can be modeled as an 8 volt source in series with 133.3 ohm resistor and a short circuit with no resistance. This means the only element controlling current in this circuit is the 133.3 ohm resistor. Ohm's law demonstrates that the circuit experiences a brief surge of 60 milliamperes of current. This is the start value for current as a function of time. Voltage across the initially uncharged capacitor starts at 0 volts. After 5 time constants, in this case 5 times 2 milliseconds or 10 milliseconds, the fully charged capacitor in contrast can be modeled as an open circuit or infinite resistance path through which no current will flow. Using this simplification, our final steady-state voltage obtained across the fully charged capacitor will be 8 volts. This is the end value for voltage across the capacitor as a function of time. Current through the fully charged capacitor will be 0 amps. Now that we have the start values, the end values, and the time constants, it's a simple matter of putting these into the time-varying expressions. Current through the capacitor as a function of time can be modeled as IC of t equals 60 milliamperes times e to the negative t over 2 milliseconds, where 60 milliamperes is the magnitude of the initial current surge and 2 milliseconds is the time constant. The plot of current through the capacitor as a function of time demonstrates that it initially experiences a spike of 60 milliamperes and then drops to 0 by 5 time constants or 10 milliseconds. Voltage across the capacitor as a function of time can be modeled as Vc of t equals 8 volts times 1 minus e to the negative t over 2 milliseconds, where 0 volts is the initial voltage, 8 volts is the final voltage, and 2 milliseconds is the time constant. The plot of voltage across the capacitor as a function of time demonstrates it starts at 0 volts and grows to 8 volts by 5 time constants or 10 milliseconds. If you wanted to, you could solve for electrical properties at specific times and solve for time values that satisfy specific conditions. As an exercise to the viewer, I invite you to solve for the instantaneous voltage across the capacitor and current through the capacitor at t equals 1 milliseconds, half a time constant, or 1/10 of the way into the charge process. Additionally, see if you can solve for the time voltage across the capacitor reaches 5 volts. At this same time, determine the instantaneous current through the capacitor. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. Substituting 1 millisecond into the voltage across the capacitor as a function of time equation yields an instantaneous voltage of roughly 3.1 volts. We could substitute 1 millisecond into the time-varying expression for current through the capacitor as a function of time. However, we can also use much simpler, more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an instantaneous 3.1 volt differential across the capacitor, Kirchhoff's voltage law demonstrates that 8 minus 3.1 of the remaining 4.9 volts must necessarily appear across the Thevenin's equivalent resistor. A quick application of Ohm's law demonstrates that with 4.9 volts across a 133.3 ohm resistor, approximately 36.4 milliamperes must be flowing through it, and by extension, 36.4 milliamperes must also be flowing into the capacitor because they are in series with one another. Let's put these instantaneous values at t equals 1 millisecond aside for later use. Our second example is asking us to determine the time the capacitor will have been charged up to 5 volts. 5 volts equals 8 volts times 1 minus e to the negative t over 2 milliseconds. What time value satisfies this condition? Most likely it'll be later than 1 millisecond because we just demonstrated that at 1 millisecond the capacitor will have been charged up to only 3.1 volts. Algebraic manipulation yields a time value of roughly 2 milliseconds. If you want to go out 3 decimal places, you're looking at 1.962 milliseconds, just shy of one time constant. We could again substitute this same time of 1.962 milliseconds into the time-varying expression for current through the capacitor as a function of time. However, we can also use much simpler, more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an instantaneous 5 volt differential across the capacitor, this means 8 volts minus 5 volts, or the remaining 3 volts, must necessarily appear across the Thevenin's equivalent resistor. A quick application of Ohm's law demonstrates that with 3 volts across a 133.3 ohm resistor, approximately 22.5 milliamperes must be flowing through it, and by extension, 22.5 milliamperes must also be flowing into the capacitor because they are in series with one another. Let's put these instantaneous values at t equals 1.962 milliseconds aside for later use. That's it. We can now map these properties back to our original series parallel circuit. Given an initially uncharged 15 microfarad capacitor, when switch 1 and switch 2 simultaneously close at t equals 0, we'd observe identical behavior for the capacitor as that we observed using the Thevenin's equivalent circuit. Notably, at t equals 0, the capacitor experiences an initial current spike of 60 milliamperes, which drops to 0 by 10 milliseconds, and voltage across the capacitor starts at 0 volts and grows to 8 volts by 10 milliseconds. Additionally, the instantaneous values at t equals 1 milliseconds and t equals 1.962 milliseconds also hold true. At t equals 1 millisecond, the instantaneous voltage across the capacitor will be roughly 3.1 volts, and the instantaneous current through the capacitor will be roughly 36.4 milliamperes. At t equals 1.962 milliseconds, instantaneous voltage across the capacitor will be 5 volts, and instantaneous current through the capacitor will be roughly 22.5 milliamperes. This is all well and good, you might say, but the obsessive and compulsive among you, like me, might be wondering what is really happening to the other elements in the original series parallel circuit. For this level of analysis, one needs to make use of series and parallel circuit properties like Kirchhoff's voltage law and Kirchhoff's current law. Additionally, one can make use of models of capacitor behavior at initial and final conditions to approximate the beginning and end of the charge process. Consider the initial conditions at t equals 0. In this case, the initially uncharged capacitor appears as a short circuit or low resistance path. This model can be used to determine the electrical properties of the remaining elements in the original series parallel circuit at t equals 0. A Kirchhoff's current law analysis of the series circuit at t equals 0 demonstrates that R1 will experience the same current as the capacitor, as no current will travel through R2, because any current bound for R2 is instead diverted through the short. No current travels through R2, and there will be no voltage across it. Given we earlier demonstrated at t equals 0 the capacitor experiences an initial surge of 60 milliamperes, this means at t equals 0, R1 must also experience an initial surge of 60 milliamperes. Ohm's law demonstrates R1 will experience a 12 volt drop. In summary, at t equals 0, Vc equals 0 volts, Ic equals 60 milliamperes, V1 equals 12 volts, I1 equals 60 milliamperes, V2 equals 0 volts, and I2 equals 0 milliamperes. The same techniques can be applied to the end of the charging process at t equals 10 milliseconds. When the charging process ends, the fully charged capacitor appears as an open circuit or infinite resistance path. A Kirchhoff's current law analysis of the original series parallel circuit at t equals 10 milliseconds demonstrates that no current will travel through the fully charged capacitor. However, current will continue to travel through the series path afforded by R1 and R2. This model of the final state can be used to determine the electrical properties of the remaining elements in the original series parallel circuit at t equals 10 milliseconds. Ohm's law for the series circuit consisting of R1 and R2 demonstrates that R1 and R2 will experience 20 milliamperes of current. Another implementation of Ohm's law demonstrates that voltage drop across resistor 1 will be 4 volts, and the voltage drop across resistor 2 will be the remaining 8 volts. In summary, at 10 milliseconds, Vc equals 8 volts, Ic equals 0 milliamperes, V1 equals 4 volts, I1 equals 20 milliamperes, V2 equals 8 volts, and I2 equals 20 milliamperes. What we've obtained by modeling the system's initial conditions and final conditions is everything we need to complete our analysis for the remaining elements, notably the start points, the end points, and the time constants. Pull the pin and throw it. For the original series parallel circuit, the electrical properties of the capacitor remain unaltered. The charging capacitor experiences an initial spike of 60 milliamperes, which decays to 0 over 10 milliseconds. Voltage across the initially uncharged capacitor starts at 0 volts and grows to 8 volts over 10 milliseconds. Current through R1 experiences an initial surge of 60 milliamperes, which decays to 20 milliamperes over 10 milliseconds. One could express this as a time-variant function as IR1 of t equals 20 milliamperes plus 40 milliamperes times e to the negative t over 2 milliseconds, where 60 milliamperes is the initial value, 20 milliamperes is the final value, and 40 milliamperes is the differential spanned over 5 time constants of 2 milliseconds each, or 10 milliseconds. Voltage across R1 experiences an initial surge of 12 volts, which decays to 4 volts over 10 milliseconds. One could express this as a time-variant function as VR1 of t equals 4 volts plus 8 volts times e to the negative t over 2 milliseconds, where 12 volts is the initial value, 4 volts is the final value, and 8 volts is the differential spanned over 5 time constants of 2 milliseconds, or 10 milliseconds total. Current through R2 starts at 0 and grows to 20 milliamperes over 10 milliseconds. One could express this as a time-variant function as IR2 of t equals 20 milliamperes times 1 minus e to the negative t over 2 milliseconds, where 0 milliamperes is the initial value, 20 milliamperes is the final value, and 2 milliseconds is the time constant. Voltage across R2 starts at 0 volts and grows to 8 volts over 10 milliseconds. One could express this as a time-variant function as VR2 of t equals 8 volts times 1 minus e to the negative t over 2 milliseconds, where 0 volts is the initial voltage, 8 volts is the final voltage, and 2 milliseconds is the time constant. This level of analysis needn't be limited to the initial and final conditions and time-variant expressions, but can also be extended into the instantaneous analysis at specific times. If you're hard-headed enough, I suppose you could substitute times of interest into all these other time-variant expressions. However, easier and far more reliable methods exist, notably series and parallel circuit properties, Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. For example, at t equals 1 millisecond, we know the instantaneous voltage across the capacitor will be roughly 3.1 volts, and instantaneous current through the capacitor will be roughly 36.4 milliamperes. We can use this instantaneous data to solve for the electrical properties of the remaining elements in the original series parallel circuit. Notably, voltage across R1, current through R1, voltage across R2, and current through R2, also at t equals 1 millisecond. If you are up to the challenge, which you should be, by all means, pause the lecture and try this on your own using only series parallel circuit analysis skills and resist the temptation of substituting 1 millisecond into the time-variant expressions. If you're struggling, here's a hint. Use Kirchhoff's current law and Kirchhoff's voltage law to determine how current flows through the system and how voltage is distributed at this point in time. If you're tracking, you should have obtained the following data. Current through elements in series is the same. Voltage across elements in parallel is the same. These are the most fundamental circuit analysis properties, and they will remain true for all applications, steady state or time variant. An application of Kirchhoff's current law to the original series parallel circuit demonstrates that t equals 1 millisecond, source current must travel through R1. Then it splits into two paths, one going into the capacitor and the other through R2. Source current equals I1, which equals IC plus I2. We know at t equals 1 milliseconds, IC happens to be 36.4 milliamperes. This is one known piece of a larger puzzle. An application of Kirchhoff's voltage law for this loop in red demonstrates that the rise induced by the source is equal to the voltage drop across R1 plus the voltage across the capacitor, E equals V1 plus VC. Another application of Kirchhoff's voltage law for this loop in orange demonstrates that the rise induced by the source is equal to the voltage drop across R1 plus the voltage drop across R2, E equals V1 plus V2. Finally, another application of Kirchhoff's voltage law for this loop in yellow demonstrates that the voltage across the capacitor will be equal to the voltage drop across R2, Vc equals V2. These analyses imply that the capacitor and R2 are in parallel with one another, and the instantaneous voltage across them will be the same. We happen to know at t equals 1 milliseconds, the voltage across the capacitor is 3.1 volts. This is yet another known piece of a larger puzzle. This implies at t equals 1 milliseconds, V2 also equals 3.1 volts. An application of Ohm's law demonstrates that R2 will draw roughly 7.9 milliamperes of current. Given we know IC to be roughly 36.4 milliamperes at t equals 1 milliseconds, an application of Kirchhoff's current law demonstrates that R1 must be experiencing 7.9 plus 36.4, or roughly 44.3 milliamperes of current. An application of Ohm's law demonstrates that R1 will experience a voltage drop of roughly 8.9 volts at t equals 1 milliseconds. Let's check our work. If both Vc and V2 equal 3.1 volts, and V1 equals 8.9 volts, does the summation of these two equal the rise induced by the source? Indeed they do. 8.9 volts plus 3.1 volts equals 12 volts. In summary, at t equals 1 milliseconds, Vc equals 3.1 volts, IC equals 36.4 milliamperes, V1 equals 8.9 volts, I1 equals 44.3 milliamperes, V2 equals 3.1 volts, and I2 equals 7.9 milliamperes. Again, if you're hard-headed enough, I suppose you could have substituted 1 millisecond to do all these other time-varying expressions to obtain this same instantaneous data. However, there's a far greater chance of you getting a wrong answer using these more complicated expressions. I am sincerely recommending you limit yourself to the application of easier and more reliable skills you've had ample practice with by now, notably series and parallel circuit properties, Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. As a challenge to the viewer, I invite you to solve for the electrical properties of the remaining elements in this series parallel circuit, notably voltage across R1, current through R1, voltage across R2, and current through R2 at t equals 1.962 milliseconds, an occasion in which we know the instantaneous voltage across the capacitor to be 5 volts and instantaneous current through the capacitor to be roughly 22.5 milliamperes. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. At t equals 1.962 milliseconds, Vc equals 5 volts, as does V2 because they are in parallel with one another. This means the remaining 12 volts minus 5 volts, or 7 volts, must appear across R1. An application of Ohm's law demonstrates that R1 experiences 35 milliamperes of current at t equals 1.962 milliseconds. This would also be the source current for this system. If we know IC to be 22.5 milliamperes at t equals 1.962 milliseconds, an application of Kirchhoff's current law demonstrates that R2 experiences 35 minus 22.5, or the remaining 12.5 milliamperes of current. Let's check our work. An application of Ohm's law demonstrates that with 5 volts across a 400 ohm resistor, it would indeed draw 12.5 milliamperes of current. Let's try another illustrated example problem. This one not nearly as detailed as the last. All I want you to do is come up with Thevenin's equivalent circuit seen by this capacitor and then model the charge process for the capacitor. The circuit consists of a 24 volt DC source, a switch that closes at t equals 0, R1 a 250 ohm resistor, R2 a 750 ohm resistor, R3 a 500 ohm resistor, and a 12 microfarad capacitor. To keep this problem interesting, note the capacitor is initially charged up to negative 5 volts at t equals 0. If you need a task list, here it is. Determine the Thevenin's equivalent circuit seen by the initially charged capacitor. Determine the time constant for the charging process. Determine the initial conditions for the capacitor. Determine the final conditions for the capacitor. Determine the time-varying expressions for voltage across the capacitor and current through the capacitor. And finally, draw plots of voltage across the capacitor and current through the capacitor for a full charge of 5 time constants. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. The Thevenins equivalent circuit, seen by the initially charged capacitor, is an 18-volt DC source in series with a 687.5 ohm resistor. The time constant for the Thevenins equivalent circuit is 8.25 milliseconds. At t equals 0, voltage across the initially charged capacitor is negative 5 volts. An application of Kirchhoff's voltage law demonstrates that 18 volts minus 5 volts, or a 23 volt differential, appears across the Thevenins equivalent resistor at the onset of the charging process. An application of Ohm's law demonstrates that the capacitor experiences an initial surge of approximately 33.5 milliamperes of current. After 5 time constants, in this case 5 times 8.25 milliseconds or 41.25 milliseconds, the fully charged capacitor will experience an 18 volt differential. Current through the fully charged capacitor will be 0 amps. Current through the capacitor as a function of time can be modeled as IC of t equals 33.5 milliamperes times e to the negative t over 8.25 milliseconds, where 33.5 milliamperes is the magnitude of the initial current surge and 8.25 milliseconds is the time constant. The plot of current through the capacitor as a function of time demonstrates it experiences an initial spike of 33.5 milliamperes and then drops to 0 by 41.25 milliseconds. Voltage across the capacitor as a function of time could be modeled as Vc of t equals 18 volts minus 23 volts times e to the negative t over 8.25 milliseconds, where negative 5 is the initial voltage, 18 volts is the final voltage, 23 volts is the initial differential, and 8.25 milliseconds is the time constant. A plot of voltage across the capacitor as a function of time demonstrates that it starts out at negative 5 volts, crosses 0 volts and into positive territory at some as of yet unknown time, and then grows to 18 volts by 41.25 milliseconds. Using these plots and time-varying expressions, one could solve for electrical properties at specific times and solve for time values that satisfy specific conditions. As an exercise to the viewer, I invite you to solve for the instantaneous voltage across the capacitor and current through the capacitor at t equals 10 milliseconds, just a little past one time constant into the charge process. Additionally, see if you can solve for the time voltage across the capacitor reaches 0 volts. At this same time, determine the instantaneous current through the capacitor. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. Substituting 10 milliseconds into the voltage across the capacitor as a function of time equation yields an instantaneous voltage of roughly 11.2 volts. We could substitute 10 milliseconds into the time-varying expression for current through the capacitor as a function of time. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an instantaneous 11.2 volt differential across the capacitor, this means 18 minus 11.2, or the remaining 6.8 volts, must necessarily appear across the Thevenins equivalent resistor. A quick application of Ohm's law demonstrates that approximately 10 milliamperes of current must be flowing through the Thevenins equivalent resistor, and by extension, 10 milliamperes of current must also be flowing into the capacitor because they are in series with one another. Our second example is asking us to determine the capacitor has been charged up to 0 volts. 0 volts equals 18 volts minus 23 volts times e to the negative t over 8.25 milliseconds. What time value in milliseconds satisfies this condition? Most likely it will be much earlier than 10 milliseconds because we just demonstrated that at 10 milliseconds the capacitor will have been charged up to 11.2 volts. Algebraic manipulation yields a time value of roughly 2 milliseconds. If you want to go out 3 decimal places, you're looking at 2.022 milliseconds, extremely early in the charge process. To solve for instantaneous current at this same time, we could again substitute the same time of t equals 2 milliseconds in the time-varying expression for current through the capacitor as a function of time. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an instantaneous differential of 0 volts across the capacitor, this means 18 minus 0 volts, or the remaining 18 volts must necessarily appear across the Thevenins equivalent resistor. A quick application of Ohm's law demonstrates that approximately 26.2 milliamperes of current must be flowing through the Thevenins equivalent resistor, and by extension, 26.2 milliamperes must also be flowing into the capacitor because they are in series with one another. Alright, if you survived that last illustrated example with your sense of dignity still intact, I hereby promote you to the rank of Guppy. This should fill you with a feeling of not necessarily pride, but rather less shame, for not only did this problem test your understanding of the capacitor charging process featuring Thevenin's theorem, but also tested your understanding of the capacitor charging process featuring an initial condition. Good work, Guppy. Good night, Guppy. Sleep well. I'll most likely kill you in the morning. Wait. Bonus round. I hereby present all you motivated Guppies angling to get promoted to the rank of Guppy First Class this challenge. Given the behavior of the capacitor, as demonstrated using the Thevenin's equivalent circuit, see if you can use your understanding of series parallel DC circuit analysis to determine the following. Determine the initial conditions, the final conditions, and the time-variant expressions for the remaining elements in the original series parallel circuit. Notably the voltage across R1, the current through R1, the voltage across R2, the current through R2, the voltage across R3, and the current through R3. Additionally, solve for the instantaneous values for all these properties at exactly t equals 10 milliseconds. If you recall, this is an occasion in which we know the instantaneous voltage across the capacitor to be approximately 11.2 volts, and instantaneous current through the capacitor to be approximately 10 milliamperes. Finally, solve for the instantaneous values for all these properties when voltage across the capacitor happens to be exactly 0 volts at t equals roughly 2.022 milliseconds. This is an occasion in which we know instantaneous voltage across the capacitor to be exactly 0 volts and instantaneous current through the capacitor to be approximately 26.2 milliamperes. If you're struggling with this bonus round exercise, here's a hint that you should not need. Make use of the previously obtained values for the capacitor at the initial, final, and specific instantaneous time states, and then use Kirchhoff's current law and Kirchhoff's voltage law to determine how current flows through the original series parallel circuit and how voltage would be distributed within it at specific points in time. You are on your own now, Guppy. These series parallel analysis skills are well within your reach. Good luck. I'll try to place the answers to the bonus round challenge in the information section associated with this lecture. In conclusion, we examine slightly more sophisticated capacitor charging scenarios necessitating the use of Thevenin's theorem. We learned the Thevenin's equivalent of a more complicated series parallel circuit can be used to simplify the analysis of the transient capacitor charging process. The electrical properties determined using the Thevenin's equivalent circuit can then be mapped back to the original more complicated series parallel circuit should the desire and motivation arise. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.